All right, let's recap what we've done. I've got a charge 2. Charge 2 is being attracted by charge 1 because charge 1 is negative, charge 2 is positive. I've got charge 2 being attracted to charge 3 because charge 3 is negative and charge 2 is positive. We've labeled out the separation between charge 1 and charge 2, the separation between charge 2 and charge 3. And so far, we've got this free body diagram that's developing on charge 2 because of attraction to the top charge and attraction to the bottom charge. And we've even developed a reference frame where we're going to call up negative and down positive. And then we're switching over to talking about free body diagrams generating an equation for ourselves. So force of 1 on 2 plus force of 2 on 3. And then expanding out what force of 1 on 2 and force of 2 on 3 would have, or 3 on 2 would have to be in terms of Coulomb's law, that law of attraction between point charges. Now comes the reference frame. So I said this once before, that if I have a positive times a negative charge, it's always going to generate a negative answer. Positive times a negative charge is always going to generate a negative answer. The negative answer just means that those charges are attracting. So what I'd like to do in terms of my free body diagram is I've got to find the absolute value of those two forces. And then I say, oh, look, it's only force of 1 on 2 that's pointing in the negative direction, right? So once I've absolute valued the force to find just its magnitude, this guy gets a negative sign. So I have to use my logical brain to think about which of these forces is in the negative direction. The other one doesn't get a negative sign because it's pointed in the positive direction. And then I can sub in my values. And I'm going to go all the way over to the left-hand side of the page here. Force F net acting on 2, oh my gosh, negative. And then I got to plug in all kinds of scientific notation. And I can't get around that. Can you guys notice? Actually, I don't even have to plug in all kinds of scientific notation. I eased up on this. I switched these charges from microcoulomb scale to coulomb, which is ridiculous because it would be like 3 bottles of lightning just kind of sitting there. Like, this is not really... I don't know why we would put 3 enormous capacitors like side by side like this, because that's probably what this would actually be. So I guess we don't have a bunch of scientific notation because I was trying to be nice to myself. Well, nice to you, I guess. Make sure you got the right charges. And make sure you grab the right radius of separation. And somehow I find that when it's charges, people seem to lose track of it more than when it was masses. I don't know why it is, because it's really just it's the same idea as if I had an array of masses that were experiencing gravity relative to one another, but people get mixed up for some reason. Yeah.
The second Q2, 0.3, and like.
Oh, did I write it as 0.3? This should be 0. Thank you. 0.03 and 0.02. You're right.
Isn't it 0.02?
If it's Q2 times Q3, I guess the order wouldn't matter. But yeah, the decimal place bit, thank you. I definitely messed that one up. Now, if we're playing the did you get the answer right game, the answer is got those 4 digits as the first 4 digits, but not in that order. So 6115, but not in that order. What'd you get?
1.562500.
1.15, yeah? Like this?
Yeah.
Yeah? 2500?
7.
Yeah, I got 7. Now, that magnitude alone should tell you that a coulomb of charge is a heck of a lot of charge. And you're right, it should be a negative value. You're right. But if you have 10 million newtons on your hands, probably, and look, these aren't even like whole coulombs. These are like on the order of hundredths of a coulomb. That's a lot of force. That tells you that you probably didn't develop that amount of charge on your sweater last time you rubbed a balloon on it, right? Because if there's that many newtons of force every time you rub balloons on sweaters, you would never get that balloon off the wall. True? Like, this is crazy. So this is a nice indicator that electrostatic force is really, really strong. Not only that, but hey, you notice that the big G coefficient is 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared. And I know that that's not the same thing as the K value, but we've already recognized that there's a similarity in the formula. Look, if on the scale of 1/100ths of a coulomb can create 10 million newtons of force, you guys recognize that that many grams of mass does not create that much force. And the reason is this G value has a 10 to the power of negative 11 in it. Negative 11, my goodness, as opposed to 10 to the power of positive 9. These guys are off by a factor of 10 to the power of 20 in terms of their scaling. That's why we couldn't rip this balloon off the wall if it had this amount of force and so little charge, really. But you can still jump up in the air and you're definitely more than 0.01 grams, right? Like, I mean, this is a big scaling difference. So, throwing that out there, that's something that we notice. We also notice, however, that gravitational force seems to extend over large distances, despite its minuscule effect, whereas electrostatic force doesn't seem to do that, right? So, I mean, there's a scaling difference in terms of how far it reaches, too. So let's scale this, or also round this off to two significant figures. So negative 1.2 times 10 to the power of 7 newtons. And I guess the best direction to call this is up, because that was the reference frame we gave ourselves. And we don't have any therefore statement because we don't have a lot more scenario, but I guess we could say therefore the net force on charge 2 is I shouldn't have said negative because I just said up was the negative, is 1.2 times 10 to the power of 7 newtons up. Sorry, I can't put the negative as well because that's redundant.